Okay, so today what we're going to be doing is I'm going to do a review with you on nuclear decay. So this is going to include alpha, beta, and gamma decay, as well as half-life. So what we're going to do is we're going to just go over some of the properties. You guys are going to do a review packet as well. So alpha radiation, okay, so alpha is represented by this, okay, and an alpha particle looks like this, 42He, okay? So what an alpha radiation does basically is it decreases your atomic number by 2, okay? And it decreases, I don't know why I'm writing it out, decreases mass by 4, okay? Now, this is the least penetrating, okay? So it's not very dangerous. It can be blocked by paper. Okay. So let's take a look at, and let me do an example. So let's say we have EU, okay, 63 is its number, and then we've got, we'll say it's 150 here, okay, and it's going to undergo alpha radiation. Okay, so its mass is going to decrease by 4, so it's going to be 146. My atomic number is going to decrease by 2. It's going to become 61. I have to look at my periodic table to figure out what's at 61, and it's promethium, PM. And now I need to show my alpha particle, 42He. Okay. Next, we've got beta decay. Beta is represented by this. A beta particle looks like this, 0, -1E. And what it does is it increases atomic number by 1. And the mass stays the same. This has medium penetrating power. And it can be blocked by aluminum foil. Okay, so let's do an example. Okay, so let's say I've got terbium, TB. That's a fun one. TB, its atomic number is 65, and let's say its mass is 170. Okay, and it's going to have beta radiation, so 0, -1E. Okay, well, I'm going to say, all right, well, my atomic number is going to change. My atomic number is going to change, but my mass is not going to change. So my mass is going to stay 170, and my atomic number is going to go up 1 to dy. So it's going to become 66 dy, which it's called dysprosium. Okay. Gamma radiation, gamma looks like this. And gamma, it doesn't give off any kind of particle. It's actually just a form of energy. So you just do 0, 0, y. It doesn't affect any kind of numbers. So does not change the element. Okay. It's blocked by lead or cement. And it has a very high penetrating power. Okay, so let's say we're going to have gamma decay happen with proactinium. So let's say we have 91, 183 proactinium, and it's going to undergo gamma decay. If it's going to undergo gamma decay, it's going to stay the same, 183, 91 proactinium. Then we're going to have this gamma be given off. Okay, so now let's do some practice problems. They're over here on this side. Okay, again, feel free to pause the video as often as you want to be able to take notes or to just pay attention, okay? So here we have to figure out what kind of reaction is this first. Is this alpha, beta, or gamma? Well, let's take a look, and I'm going to zoom in a little bit here. My atomic number is going from 238 to 234. So it's decreasing by, not my atomic number, my mass. My mass is decreasing by 4. And my atomic number is decreasing by 2. So that, to me, looks like an alpha particle, and it is. This is alpha radiation. Okay. This next problem, my mass is staying the same. It's 234 to 234, so I'm not going to change that. My atomic number is increasing by 1, which means we're subtracting a -1. So here we go. Okay. So this is going to go, it went up 1 step to proactinium. So that means this is one of those beta particles. So this is beta radiation. Okay, for this one, we know that it's alpha radiation because we have this 42He. Okay, so we are going to decrease our atomic number. So I'm going to write down alpha radiation. We're going to decrease our atomic number by 2. So 91 minus 2 is 89. We got 234. It's going to decrease by 4. It's going to be 230, 89. Look at 89 on my periodic table, and I see that it's AC, actinium. Okay, so that's alpha radiation. Number 4, another alpha particle right here. So 220 and 86 radon. So 86 is going to become 84. 220 is going to become 216 because it's going down by 2. Okay, 84, who's 84? Polonium on my periodic table. Okay. Oh, look, we got polonium in the next problem, and this was alpha as well. Okay. So number 5, we got here, this is showing us that we have beta radiation. This is beta because that's a beta particle. That should be a T. So this number is not going to change. It's going to stay 216. The number 84 is going to go up to 85. And that's going to be astatine. Okay, you're going to need a periodic table for this, guys. Okay. Next, let's see. Our mass is staying the same. Our atomic number is increasing by 1. So I'm going to put an E here because it's going to have to be one of those beta radiations. Beta decay. All right, this one's telling me that I want to do gamma decay. That's what it's saying right here, gamma decay. So my substance isn't going to change. It's going to stay 210-83 bismuth. But I'm going to give off a gamma ray. Okay. Remember, it's only energy. It's not actually a particle. So that's the decay reactions. Now we're going to talk about half-life. So what is half-life? Well, it's the amount of time it takes for half of a radioactive substance to decay into another. Let me pause for a second. So now we've got the half-life of cobalt-60 is 5.26 years. If 100 grams are left after 15.8 years, how much was in the original sample? Well, we're given a half-life and we're asked for the amount of our original sample. So we're going to have to work backwards from the amount that we're given to figure out how much we began with. Okay, so let's figure out, first of all, how many half-lives did we have? Well, I know that 15.8 years have passed. The half-life is 5.26 years. So that's 3 half-lives. So now I only have 100 grams left, but 3 half-lives have passed. So what I'm going to need to do is multiply this 100 grams by 2 3 times, okay, for those 3 half-lives. And it turns out that I started with 800 grams. And that's the answer to this one. Okay, so we solved from the amount that we remained with to our amount that we started with. Okay. For the next one, we've got actinium-226 has a half-life of 29 hours. If 100 grams of actinium decays over a period of 58 hours, how many grams will remain? So now we're looking for how much is going to be left. Okay. So it's different from the first one. In the second one, we need to find out how many half-lives have passed and then decrease it by that amount. Okay, so 58 hours have passed and the half-life is 29 hours. So it's 2 half-lives. So we're going to take our 100 grams and we're going to cut it in half twice. So we're going to have 25 grams remaining. Okay. Whoa! Okay. All right, so this actually has the wrong number here, 5730. I think it's fixed on your paper. Carbon-14 is used to determine the age of long dead, once living things. The half-life of carbon-14 is 5,730 years. If a Neanderthal is found to be 28,650 years old, what fraction of the original amount remains? So we're looking for a fraction, okay? So first let's figure out, okay, how many half-lives is that? That's a really long time, 28,650 years. 28,650 years divided by 5,760 years and a half-life. That's 5 half-lives. So I'm going to do 1/2 times 1/2 times 1/2 times 1/2. 1, 2, 3, 4, 5. Okay. So in my calculator, I'm going to do 2 times 2 times 2 times 2 times 2. So 5 times I'm going to do it. Okay. It's going to get me 32. So 1/32 of the original amount is going to remain here. Okay. All right. So remember, we're asked here for the fraction. So that's why I did it this way. I wasn't asked for an amount because I wasn't even given an original amount. Here we have the remains of an ancient bird are found. Scientists estimate that it originally contained 80 grams of carbon-14, but now only 10 grams remain. The half-life is 5,730 years. How long ago did it die? Well, I was given an original amount, and I'm given now my final amount. So here's what I'm going to do. I'm going to take my original amount, 80 grams, and cut it in half, 80 to 40 to 20 to 10. Now I'm going to see how many half-lives that is. That's 1, 2, 3 half-lives. Okay, so if it's 3 half-lives, and so 3 half-lives, I don't want to say that half, 3 half, because it looks like 3 1/2. 3 half-lives times 5,730 each, 5,730. That gets me 17,190 years old. So to solve these kind of problems, to solve the ones that we went over previously, the decay problems, you're going to need a periodic table. For these kind of problems, you need to be thinking about, okay, what does half-life mean? What is this question giving me? What is this question asking me for? Okay, so the questions that you're going to be working on your practice packet should be modeled similarly to one like this. Okay. All right. If you have any more questions, shoot me an email. Thank you.